Anthony starts at the beginning of a flat road and rides his skateboard at a constant speed of 9 meters per second for 13 seconds until he approaches the bottom of the hill. He rolls up the hill to a point 6 meters from the bottom of the hill before he starts rolling back down and onto the flat piece of road again. How long is the flat stretch of road? How long did it take Anthony to reach his highest point on the hill? How long was Anthony on the hill altogether? All right, I thought it would help to just have a little demonstration of what's going on here. Here's the flat part of the road. Here's the hill. Anthony's skateboard over here is going to coast along the flat part of the road before it rolls up the hill, comes to a stop, turns back around, goes down the hill, and then continues back onto the flat piece of road, just like this. Alright, so the first thing you should be realizing here is, well, he's going at a constant velocity on the flat part. Then he's accelerating on the hill. He's going to slow down, then speed up. That means constant velocity over here, non-constant velocity over on the hill. His acceleration is not constant throughout the entire problem. Newton derived all of our kinematics equations with the assumption that acceleration would be constant throughout the problem. It's not here. That does not mean you get to turn off the video and go do something else. What it means is we're going to split the problem into two parts. And by doing that, we have two mini problems. And what you'll see is that the acceleration is constant on the flat section. And then, that problem aside, the acceleration is constant the entire time that Anthony's on the hill. So that's how we can approach this problem, even though the acceleration is not constant the entire time. So, let's just start with the flat section. If you go back and read the problem, and again I apologize, I can't fit the problem on the board. So go back to the beginning of the video if you need, take a screenshot, whatever you want of the problem, and then come back to this point. If you go look at the problem, it starts out with Anthony moving at a constant speed of 9 meters per second. And he does that for 13 seconds. On the flat part of the road. And that's all I'm going to do. I'm not even going to worry about the hill right now. The hill does nothing for me. And then the first question asks, how long is the flat stretch of road? So, I'm just going to focus on that. It tells us that while he's on the flat part of the road, he's traveling at 9 meters per second in a straight line. And it tells us that he's doing that for 13 seconds. And then the first question it asks is, how long is the flat stretch of road? So we're going to find how long it is, or how far he travels. So delta x. So we're just going to write down our given. And we know that his velocity is 9 meters per second. And we know that it takes him 13 seconds. And we're going to find his displacement, which will tell us how long the road is. So we're just going to use our basic equation. I can use this average velocity equation because we know the velocity is constant here. And so if he has a constant velocity of 9 meters per second, then his average velocity is obviously 9 meters per second. We're going to solve for x, so I'm going to move delta t over. And then we're just going to plug in our numbers. So we get 13 times 9 equals delta x. 13 times 9, let me just go check and make sure I get it. 107. Part 1, done. Easy. And again, the key to that was we ignored the hill altogether. Yes, Anthony has some acceleration on the hill. We just don't care while he's on the flat section. Now we can move on to the hill part. So when he's on the hill, we know he gets to the bottom of the hill, coasting along here. So at the bottom of the hill, his initial velocity is 9 meters per second. Because that's how fast he was going on the straight part. He just got onto the hill. So he hasn't had time to slow down yet. And then he's going to coast up the hill a little bit. And if we go back and look at our problem, it tells us he rolls up 6 meters from the bottom. So he rolls 6 meters up the hill, at which point he stops. And that's what you have to realize, that if he's going to roll up the hill, he's going to go get slower, 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 and then stop at the very top, and then he'll turn around and go back down the other way. We'll catch it this time. So, there's our VO and there's our VF, and that's very important. And then it asks how long, the next question is, how long does it take for him to get to the highest point? He stops at the highest point. So I'm going to write down my given. We know that VO is 9 meters per second. We know that VF is 0. We know that delta X is 6 meters. And the question is, how long did that take? Going to our list of kinematics equations, we're going to use one that actually comes from this. I'm going to use the equation delta X equals VO plus VF over 2 times delta T. Average velocity times time equals displacement. And then what we're going to do is we're going to plug in our numbers. We already know VF is 0. We're not going to bother with that. What am I doing? Can't plug in our numbers yet. We haven't solved for delta T. We're looking for delta T. I apologize. So what we're going to do is we're going to move this whole mess over to the other side. If you want, you can simplify it a little bit. To that, because VF is equal to 0. And then we're going to move the 2 over. We're going to move the VO over. So you get 2 times delta X equals VO times delta T. And then we're going to move the VO over by dividing everything by VO. So we get 2 times delta X over VO.
1, 2.
Testing. Equals delta T. That's our equation solved for delta T. Now we can plug in our numbers. 2 times 6 over 9. That's 12 over 9, which sounds like 1.333. So that'll tell you how long he was on the hill, how much time it took him to get up to the top of the hill. The next question is, how long was Anthony on the hill altogether? Well, we could do a lot of math. We could write down some more given. We could use another equation that would look very similar. Or, what we could do instead is realize that it took him 1.33 seconds to roll up the hill. So he started here, 1.33 seconds later he was stopped at the top of the hill. At that point, he's going to start rolling back down. That was better. So he starts rolling back down the hill from here. It's going to take him the same 1.33 seconds to roll back down the hill that it took him to roll up the hill and stop. So all you have to do is do 1.33 times 2. You get 2.66 seconds. That's how long he was on the hill altogether. And that's it.